மகேந்திர சிங் தோனிக்கு பாத்தீங்கன்னா கேப்டனுக்கு ஓரளவு புஷ்வேல் இருந்து பாத்தீங்கன்னா நம்பர் 4, நம்பர் 5 அந்த மாதிரி இடத்துல அவங்க விளையாடிட்டாங்க. ஸோ அவர் அப்படி ஆர்டர் வருது ஒரு நல்ல நியூஸ்
Okay. Hello. Good morning, guys. Long time. How are you?
Fine, sir.
Huh.
Good morning.
So, good morning. So, I think there is a new student with us today. I think it's Rahul. Hi, Rahul.
Hi, sir.
So which school are you from, Kanna?
DAV.
DAV. Okay. So, how is it going?
Fine,
Exams
sir.
got over?
Yes, sir.
Okay, fine. So, you can go through all the videos before, right? We have
Yes, sir.
completed 5 chapters. So this is the 6th chapter which we'll be completing today, right? And if you have any doubts, my friends will have my number, right? So you can text me if you have any doubts, or say give me a call, right? Or else whatever form, like if you have
Okay, sir.
any doubts, we can clarify it, right? If we can
Okay,
have
sir.
any personal session if you want. Is it okay?
Okay, sir.
Cool. Okay. So people, how was your exams? Some of you had school exams. How was it? No exams.
Sir, mostly examples only, sir. Sorry, sir. Mostly MCQs, sir. 18
Mostly
MCQs.
MCQ.
Yes,
Okay.
sir. In that MCQ, one-word questions and multiple choice questions
Okay.
came, sir. And they asked just about 5 questions, sir. Two
Assertion and
sums,
reason.
two sums,
Sorry.
and
Assessment and reasoning.
sir.
Assertion and reasoning, sir.
That
Assessment and reasoning.
18
Okay.
one more questions. Sir.
Okay. Okay. So was it easy?
Yes, sir.
Okay. Fine. So people, I know it's been a long time since we met, right? So hope you remember what we're speaking about. Okay. What chapter are we in? Huh? What chapter are we speaking about? People?
States of matter.
Okay. Thank God. So it is states of matter or gaseous state, right? Fine. So what were we speaking about when we left?
We're talking about ideal gas.
Were we talking about ideal gas?
Boil temperature.
So we were speaking about real gases, right? And we saw how real gases are deviating from ideal behavior, right? So we saw in the form of a graph, P versus V graph, right? We know what kind of graph we expect for an ideal gas, but what kind of graph we are getting for real gas, right? And then we went on to see what is the quantification of the deviation, how much deviation is happening, right? And for that I had a factor. What is the factor called as? There was one factor which determines how much deviation is going to happen from the real gas and ideal gas. What was the factor?
Compressibility factor.
Good. Right. What is the formula? Okay, compressibility factor was what letter? What is the representation?
Z.
Z. Okay. So Z is equal to what? Nobody remembers. So everybody was so busy preparing for their exams that they forgot this chapter because this chapter was not taught in school. Because obviously we're preparing for other chapters. Okay, fine, I understand. Right. So Z, this compressibility factor is PV by RT, and this V is V real, right? So PV by RT we say, correct? So this was my compressibility factor, right? Or I can even write it as what? V real by V ideal, that is the real volume divided by the ideal volume, or I can even write it as P real divided by P ideal, right? So if you can remember all these formulas were the formulas for compressibility factor, right? So we know for an ideal gas, Z is equal to for an ideal gas, what is the value of Z?
1, sir.
Correct, right? For an ideal gas, obviously I know PV is equal to RT. If at all I have 1 mole of a gas, right? So I can say that Z is equal to 1 for an ideal gas, right? And we saw sometimes Z was less than 1 and sometimes Z was greater than 1 in the graph. You could have seen the graph would have come like this. There's a dip and then that again increases. Correct. Okay. So Z less than 1, what does it implicate?
Sir, could you repeat?
I was saying you should have seen the graph, right? The graph,
Yes, sir.
this is Z is equal to 1 graph. This is Z versus V or Z versus T graph. For this is for an ideal gas. But what we saw for real gases, some of the gases would have been like this, right? So you can see that at this area, Z is less than 1. And obviously in this area, I know Z is greater than 1. What does it implicate? What does it tell you about the real gas? In these two regions.
Less than 1 means attractive force is greater.
Good, right? So in your kinetic theory of gases, which defines what is an ideal gas, there were few problems. Correct. There were few assumptions which were wrong. So what were the assumptions? The first assumption is, what were the assumptions which are wrong in KTG? There are two assumptions which are completely wrong. What were they?
The volume of gas particles.
Correct, right? So first is about the volume of the gas particles are negligible. So kinetic theory said that volume of individual gas particles are negligible when compared to the entire volume of the gas. That's why we say it as point masses, right? So compared to one single gas's volume, and if I compare it with the entire volume, that volume of individual gas particles are negligible, and that is wrong, right? Okay, why is it wrong? Why did we say it is wrong? How do we prove it?
Through liquefaction.
Correct, right? So obviously all gases can get liquefied, and obviously if that particular gas can get liquefied, I know liquids will have definite volume, right? So definitely if liquids have definite volume, where it is coming from? It is coming from the gas. So gas molecules also should have some volume, right? Individual volume. Okay. What was the second point, which was wrong?
Attractive or repulsive force.
There's no
Correct.
force of attraction between the molecules.
Correct, right? So KTG said that there is no interaction, there is no force of attraction, there is no force of repulsion between the gaseous particles, right? But again, the same liquefaction explains you that if I can convert gas to a liquid, in liquid I have more force of attraction, that means definitely there should have been some force of attraction or repulsion for that matter between the gaseous molecules, right? Okay, and that exactly is what my Z less than 1 and Z greater than 1 are speaking about, right? So what we said, if I say that the Z is less than 1, right, that means the real pressure would be lesser than the ideal pressure. What does that mean? That means someone is pulling the gas molecules from behind. That is the attractive force. So it will go hit the walls of the container with lesser force, means lesser pressure, right? So obviously we have to understand that this area where Z is less than 1 indicates that the attractive forces are dominating, right? And obviously when I have less Z greater than 1, that means the real pressure is greater than the ideal pressure. That means someone is pushing the gas molecules from behind, and the gas molecules are going to hit the walls of the container with a greater force and obviously greater pressure. And that's what is being indicated here, right? Okay, so this is all the things we saw, and obviously I told you that if I if I draw the graph again, right, this is Z is equal to 1. So this is at temperature T1. Now this is at temperature T2. And this is at temperature T3 and temperature T4, right? So can you arrange T1, T2, T3, T4 in ascending or descending order? Which is greater, which is lesser? So the same gas, assume that all are O2 or N2 at different temperatures, right? If we, how will you arrange T1, T2, T3, and T4? Which is greater, which is lesser? Any guesses? Obviously, right? There can be only either T4 is greatest or T4 is least. What is that?
T4 is least.
No. So T4 is the greatest and T1 is the least, right? So what we said here, as we keep on increasing temperature, right? As we keep on increasing temperature, the dip, right? The Z is the Z less than one curve. The Z less than one portion keeps on less pronounced, right? So you can see at T4 there is literally no area behind. There is literally no area beneath Z is equal to one curve, right? So what is the temperature called as? Someone just said, like, when I asked you.
Boil temperature.
Correct, right? So this particular T4 is what is my boil temperature, right? So what is boil temperature?
Temperature at which real gases behave like ideal gas.
Sorry. Right. So yeah, so boil temperature is the temperature at which real gases behave ideally, not for entire this thing, but for a limited range of pressures. So if I plot this with Z versus T, you can see that this entire area, that entire pressure region, in that pressure region and at that temperature, the real gases behave ideally. Why they behave ideally? You can see that they are coinciding with Z is equal to one curve, which is for an ideal gas, right? So I think this is where we stopped. Correct, right? So we'll move on, right? So we will move on to see how am I going to correct, right? How am I going to correct all these things? We understood that definitely real gases are not going to behave ideally, and we even understood why they are not behaving ideally, and how much will be the deviation. All these things we saw. Now is the right time to correct the equations, right? So we have PV is equal to nRT for an ideal gas, and this equation is not going to work for us anymore because we saw so many problems, right? So there was this guy called Van der Waal, and we know what is Van der Waal. Van der Waal we have already heard so many times. Van der Waals forces, Van der Waals this thing, that thing, right? So this Van der Waal, right? Van der Waal gave an equation, right? So this is just a modification of this particular equation, right? So that it can work for real gases, right? So this equation is also called as Van der Waals equation, or it is also called as real gas equation. Okay, so very simple. He just there is a derivation for this, but again, you are not required to know the derivation. You are just required to know what is the equation itself, right? So this is how the equation goes. So okay, before all this, right? Tell me, generally, at what conditions, right, real gases can behave ideally? At what conditions real gases can behave ideally?
When temperature is high,
Good. Okay. Then
volume of the gas should be great.
volume. No. Volume we cannot speak. We should speak in terms of temperature and pressure, and obviously volume will change accordingly. So yeah, high temperature and
Low
what
pressure.
that's it, right? So guys, how will you remember this? I told you, you just have to make sure that the the postulates, or say the points given by KTG are true, right? So obviously, how will I make it true? So if I want to make sure that the individual gas molecules are, the volume of individual gas molecules are negligible when compared to the entire volume, you have to make sure that the volume of the gas entirely occupied is very high, right? So obviously we can just go for your your Gay-Lussac's law and your Boyle's law, right? So if at all I want the volume to be very high, the pressure should be very less, right? And obviously if at all I want the volume to be very high, the temperature should also be very high. So a real gas can behave ideally at very high temperatures and very low pressures. Right? This all can be questions which can come in your exams. Right? At what conditions of temperature and pressure real gases can behave ideally, and your answer should be high temperature and low pressure. Right? Cool. So yeah, so now we can go back to this Van der Waals equation. That is the modified version of ideal gas equation. Right? So this is how the equation goes. Right? So P plus A n squared by V squared into V minus NB is equal to nRT. This is the equation. Right? So the equation might look complex, but you don't have to worry. No problems are going to come from this. Right? So you just have to know the equations. Right? So what I'm trying to do here, right? So you can see that n is number of moles that we know. So other than that, we have two more things, that is A and B. A and B are what are called as Van der Waals constants. Okay, this A and B, which I wrote here, right, are what are called as Van der Waals constants. Okay, so obviously there are two extra terms you see. If at all I don't have this, if I don't have this, I just have PV is equal to nRT, right? So these two terms, that is A n squared by V squared and NB, right, are actually the correction terms. Okay, so we already know there are two main problems in KTG. One is regarding the volume, the other is regarding the the force of attractions, right? So please understand I think A, right? A is the force constant, right? So A is for the force correction, right? We said that there is no force of attraction, right? So A is my force constant and B is for the volume correction, right? So A is force correction and B is volume correction. Okay, so that's the two main problems we had in KTG, that is kinetic theory of gases, right? So A is for the force correction and B is the constant for volume correction, right? And this exactly is what is called as my real gas equation or Van der Waals equation for real gases. Okay, right? So you just have to know the equations. There is no problem which is going to come from this. Just remember the equation. Nobody's going to ask you, like giving the AB value and asking you to calculate something. No, that is not going to happen. But they might ask you what is about A, what is B, right? So you have to tell that A and B are Van der Waals constant, where A is for force correction and B is for volume correction, and the equation. That's it. That's what you need to know, right? Fine. So moving on. So people, that is about gaseous state. Okay. So now we are going to see little things about liquid phase. Okay. No, not exactly liquid phase. We are going to talk about the transition of gaseous state to liquid state. That's what we are going to see. Liquid state is not there for you, but for JEE and NEET exams, yes, little you have about liquid state also. But even if you are not going to study, you will definitely study them about in physics, right? You will have a chapter called as what is that, fluid dynamics or fluid, something regarding fluids. What is the chapter? Did you see the chapter regarding fluids in physics?
Not yet, sir.
Not yet. So nobody even opened the book and checked what are all the chapters, isn't it? Good. That's how it should be. So anyways, so we will see how we are going to convert gas to a liquid, right? Obviously, we know there is this thing called as condensation, right? We know what is condensation by just keep on reducing the temperature, right? So obviously, gas molecules can get liquefied, that is condensed, right? But that is not what we are going to see. See, there are two ways by which I'll be able to convert a gas to a liquid, right? One is definitely by decreasing the temperature, by cooling of the gas. That I can do, right? And in most of the cases, condensation will not work. And not like in, say, good number of cases, condensation alone will not work, right? So we are going for the other method, right? The other method is by increasing the pressure, right? The other method is by increasing the pressure. And what is that process called as, people? What is the process of converting a gas to a liquid by increasing pressure? What is it called as?
Liquefaction.
Exactly. Right. So we are going to see exactly that. Right. So liquefaction. So how do I define liquefaction? It is the process of converting a gas to a liquid by increasing pressure. As simple as that. Okay. Fine. So we're going to see a graph. Okay. So we'll see how the graph will look. Right. So I have pressure versus volume graph. Okay. Okay. Fine. So what I'm going to do, right? So obviously, right. So I'm going to keep on increasing the pressure, right? At some point of time, the gas molecules are going to get converted into liquid phase. That we understand, right? So if I plot this in the form of a graph, what do you expect to see? You'll see that, right? So initially, I have very less pressure, right? Initially, I have very less pressure. Now I'm going to keep on increasing the pressure, right? And the volume is obviously going to decrease, isn't it? So initially, you can understand. Initially, I will have some amount of volume of the gas molecules, and the pressure will not be. I didn't apply pressure yet. That means I have a very less pressure. Okay. So I have very less pressure, high volume for the gas. So this is the point where I started, right? High volume, less pressure. Okay. So now if I keep on increasing the pressure, right? So what will happen to the volume? Obviously, volume is going to keep on decreasing, right? So volume is going to keep on decreasing. Okay, fine. Now at a point of time, right? At a point of time, what is going to happen is the gas molecules are going to get converted into liquid phase. Yes, right? So now at that particular moment, right? So please understand, people, if there are 100 gas molecules, right? If there are 100 gas molecules, at that particular pressure which I'm talking about, the liquefaction starts. Means one first gas molecule will go into the liquid phase. Okay, the first gas molecule will go into the liquid phase. Correct. So obviously that doesn't mean that all the gas molecules is went, right? But the moment liquefaction starts, right? So the more and more number of gaseous molecules will go into the liquid phase, right? Now at that moment, you will definitely see volume changing. Is it not there? That too, the moment liquefaction starts, you will see till this point, that is till liquefaction started, you will see a gradual decrease in volume because you are increasing pressure, right? The molecules are still in gaseous phase. So the decrease in volume is little gradual. You can see it is very gradual. Okay, but the moment liquefaction starts, but the moment first molecule goes into liquid phase, there is going to be a rapid change in volume. Obviously, right? Because I'm going for change in state now. Well, liquids have little lesser volume when compared to the gases. Correct. So the moment liquefaction starts, right, there is going to be a drastic change in volume, right? And one more thing, what you have to understand is, from the moment liquefaction starts till the moment liquefaction ends, there will be drastic change in volume, but pressure is not going to change. Please understand that, right? Now you would have seen this even in case of your boiling, right? So what happens in boiling, right? So I convert a liquid to a gas by keep on increasing the temperature. But the moment the boiling starts, the moment I reach 100 degrees Celsius, we know that the temperature and pressure is not going to change, right? If you want, you can even keep a thermometer and check, right? So you will see that the moment 100 degree reaches, right, until all the water molecules has boiled up, you will see that the temperature is not changing until that point. The temperature will become 101 degrees Celsius after all the water in the bowl has boiled up, right? The same phenomena goes here, right? So the moment when liquefaction starts, right, there is going to be a rapid decrease in volume, but the pressure is not going to change, right? So this is how the graph will look. So you will see that the pressure is not changing, but there is a rapid decrease in volume. Correct, right? So I would say this is the point where liquefaction started, and this is the point where all the gas molecules went into liquid phase, right? Okay. Now what is going to happen? Now still you are keeping on increasing pressure, assuming, right? still you are going to keep on increasing the pressure. Already you are increasing pressure now that you have completed what you wanted, but still you are keeping on increasing the pressure, right? So what is going to happen? Liquids are generally liquids, we say that we are almost incompressible. Okay, liquids are generally almost incompressible. You cannot compress liquids as you compress gases. You can compress solids, right? We can compress gases, but liquids have a very special property that they, ideally speaking, they should not get compressed, right? Okay, but anyways, you will see, definitely see some change in volume for the increase in pressure, but not like this, not like this. So you will see almost no change in volume. You can see, say for example, this is one pressure and this is a second pressure. Look at the change in volume. Very small change in volume. Okay, right? So this is how the graph will look for a liquefaction process. Okay, so please understand, this is the point where the gas was initially there, right? So I keep on increasing the pressure is keeping on increasing. Obviously the volume has to reduce, right? Now at a particular point, the liquefaction starts, at a point where the liquefaction starts, and this is the point where the liquefaction starts. I can even mark it if you want. This is my liquefaction starting, right? So when the liquefaction starts, until all the gas molecules have gone into liquid phase, there is not going to be any change in pressure, but there'll be a drastic change in volume because the phase conversion is happening, right? And obviously after that, this is the point where the liquefaction ends. All the gas molecules have gone into liquid phase, right? And obviously after that, if you keep on increasing the pressure, the volume change is negligible because I've gone to the liquid phase, because liquids are generally almost incompressible. Okay, right? So what you have to understand is, if I talk more about this particular point of the, this particular area of the curve, that is when I have the liquefaction starting, that is the region between liquefaction starting and liquefaction ending, I would say that there is going to be an equilibrium existing between your gaseous phase and your liquid phase, right? There is going to be an equilibrium existing between your gaseous phase and liquid phase. Okay, so this we need to know, right? Now, say assume that this particular curve happens at a temperature T1. Okay, this particular curve happens at a temperature of T1. Okay, right. So now if I increase the temperature, how the graph will change? We'll see. Okay, so for that I need to draw a different graph because there is so much clumsiness happening. So people, any doubts? Any doubts about the graph? Any doubts about how liquefaction happens? Is everything clear?
No doubt, sir.
Cool, right. So now we'll see, if I increase temperature, what will happen to the curve? Okay.
Sir, this graph was for a constant temperature, sir.
Yes, this is an isotherm. Correct.
Okay.
It's not one particular temperature, right? Right. So now, again, I have P versus V. So I know how the graph will look. So this, that, and this. I mean, okay, approximately. Right? Okay. Now this is the temperature T1. Okay. So now we'll see what happens with the, if I increase the temperature to some other temperature T2, right? So you will see a graph. Okay, something like, I mean, okay, this is a straight line, bear with it, right? So again, if this is a temperature T2, now again, this is a temperature T3. Now, if I keep on increasing it, you at a point, you will see that there will be almost, there is just a dip, little dip. Okay, if I'm going to keep on increasing, the graph is going to look like this. Okay, this is the temperature T4, this is the temperature T5. Okay, right. So what are you seeing? What are your observations from the graph?
There is no equilibrium.
Okay, that's the first observation I make, isn't it? So what I see is that if I keep on increasing the temperature, the point where the liquefaction starts and the liquefaction ends, there is no distinction. Basically, that region where I, as you said, the region where I have the equilibrium existing between the gas molecules are keeping on getting shorter and shorter and shorter, right? That's exactly what is happening. Okay, so at a point of time, what you see is that there is the equilibrium region just becomes a point, right? Just there's a little dip, and then again the liquid region is there. Correct, right? So obviously, and after that, what do you see? This particular curve, right? The particular curve, what do you see here? At T5. What is that? What does it indicate? In T5, what does it indicate?
There is no starting or ending.
Exactly, means
Liquefaction does not take place.
exactly, right? So that particular point after this T4, if we still increase the temperature to T5, liquefaction is not happening. Oh my God. Okay, right. So there are certain things which you have to know, people, right? So let me give you an let me give you an insight for this. Why this is happening like this? Okay, right. So say I have hydrogen gas, right? I have hydrogen gas at say some okay 25 degrees Celsius, right? The same hydrogen gas I have say at 50 degrees Celsius. Same hydrogen gas say I have at 100 degrees Celsius. Okay. Now think and tell me, right? In which case, right? In which case I have to supply more pressure for the gas to get liquefied? Do you understand my question? I'm
100
asking.
degrees Celsius.
Definitely, right? So if the see, please understand, I'm going to liquefy a gas. So obviously there has to be two things happening. Like two things in the sense, favorable conditions. What are the favorable conditions? Definitely the temperature must be lesser, right? And the pressure should be very, very high, right? So only in, I mean, these are the favorable conditions required for me to liquefy a gas, right? So if I keep on increasing the temperature, what you see is I have to apply more and more and more pressure for the gas to get liquefied. So definitely at 100, if I compare the pressure at say this requires a pressure of T1, this requires a pressure of T2, and this requires a pressure of T3 for liquefaction. Definitely T3 will be a very, very high value, right? Now if I keep on increasing this temperature, I go to 200, 300, 500, right? Now you are going to reach a point, right? You are going to reach a temperature where irrespective of how much ever pressure you give, right? Irrespective of how much ever pressure you give, you cannot liquefy the gas, right? So that is the point where we are seeing, right? There is a particular temperature after which how much ever pressure you supply, you go to even infinite pressure, you cannot liquefy the gas. Okay, and that particular temperature above which, no matter what, how much of a pressure you apply, you are not able to liquefy the gas. That temperature, that is my T4 here, is what is called as my critical temperature. Very, very important, right? So this particular temperature above which, irrespective of how much of a pressure you supply, the gas cannot be liquefied. That pressure is what is called as your critical, sorry, that temperature is what is called as your critical temperature. Did you understand, right? So everybody should have understood what is critical temperature. Again, I repeat. So if at all you want a proper definition, I can give you one. Please take down for critical temperature. It is denoted by the letter TC. So your T4 is my TC in this case, right? So please take down. Critical temperature is the temperature, or I would say, it is the minimum temperature. Critical temperature, minimum or maximum? Maximum temperature. I'm sorry. critical temperature is the maximum temperature. Critical temperature is the maximum temperature at which a gas can be liquefied. Obviously, beyond that, you cannot liquefy it, right? So critical temperature is the maximum temperature at which a particular gas can be liquefied. Okay, right? Fine. So obviously at the critical temperature, so at this point, right, you will have some pressure. At this point, I will have some volume. So this pressure and volume are what are called as your critical pressure and critical volume, right? So how will I define it? Critical pressure is the pressure at the critical temperature, right? And critical volume is the volume at the critical point. That is the critical temperature. Okay. So critical pressure, critical temperature, and critical volume, you need to know what is that, right? So that's what I need to say. Okay. You even have a formula to find out your critical temperature, pressure, and volume, but I don't know whether you have it in your syllabus. I don't think you have. Okay. So basically that comes in terms of A and B. We saw the Van der Waals constant, right? A and B, right? So I can even give you the formula if you want. It's simple. Right. So the critical volume is going to be equal to 3B. And critical temperature is 8R, 8 A, no, oh wait, 8A by 27 RT squared, RT squared? No, I'm not sure, I'm not giving you the formula which is wrong, so VC is correct. So maybe next class, I'll give you the formulas for TC and TC. TC and TC are basically critical temperature and critical volume. Okay. So yeah, that's about the chapter. Okay. So we saw gaseous state, and we saw now a little bit about how do you convert gaseous state into liquid state. Okay. What is the time? 15 more minutes, people. You can ask your doubts in this chapter or any other chapter if you have. You can ask. Any doubts?
So, sir, we can say that any real gas can be an ideal gas at an appropriate pressure and volume.
At an appropriate pressure, yeah, definitely. So we cannot say appropriate pressure. We can say that we talked about boil temperature, right? So boil temperature is the temperature at which the real gas can behave ideally for a small range of pressure. It is not one pressure. It is some range of pressures,
Okay, sir.
but at a particular temperature. Understood?
Understood, sir.
Right? Okay. Any other question? Okay, fine. So next chapter would be thermodynamics, and that is my favorite chapter. I mean, especially in physical chemistry, thermodynamics is my favorite chapter. It is very, very interesting, right? People find it a little difficult, but do not worry, right? We are going to make it very, very, very easy for you. Okay, so it's a beautiful chapter. Like you will see so many what to say. You will not even realize that basically science is even applied here. Okay, so I can give you a small example, right? So why do you think anything you do, say for example your fan is running, right, and you see that after a point of time the fan would have gotten hot, right? Or I can even say, even simply, if you just clap your hands, right, maybe you will not be able to realize it, but if you clap your hands really hard, you will see that your hands have become hot. Right? So we will be giving reasons for all of these, okay? Because there is going to be something called a second law of thermodynamics, which answers all these questions, right? And also you will be seeing a little bit about engines, right? How engines work, right? And obviously that again, if you just run a vehicle for a longer, like some period of time, again you see that the vehicle becomes hot, right? So all these things, right? And obviously we are going to predominantly go with heat, the heat flow, and different kinds of processes. All these things will be seen, right? Okay, right? And after that, we'll be going for equilibrium, right? So again, equilibrium is the last chapter where you have problems in this 11th class. Okay, so till now, what are all the chapters which comes under physical chemistry would be some basic concepts, atomic structure, this chapter, gaseous state, thermodynamics, equilibrium, anything else? Yeah. So these 5 chapters are the chapters you have in your physical chemistry part, right? So after that, after I finish equilibrium, we'll be going for general organic chemistry, right? Again, a beautiful area of chemistry. Like again, my favorite part amongst the 3, physical, organic, and inorganic, is organic, and I'll make sure that you also love that. Okay. So that will be seen. And 2 chapters we have in organic, that is general organic chemistry and hydrocarbons. So that will be seeing. And I think after that, what else is there? Your S and P block. Right. So again, that's a little boring chapter, but still, we'll see what we can do about it. Right. Okay. Right. So people, what else? Any doubts from previous chapters? Any questions which you saw in your exam which you're not able to answer? We have 10 minutes. We can use it properly. Okay. Fine. So if you don't have any questions, I can ask you questions. Obviously, that can happen. Right. So let me ask. From which chapter do you want it? Okay, that also I'll decide. Okay, so I have I3 minus. Okay, I want you to tell what is the hybridization, what is the shape of this molecule. Oh, not molecule, ion. I have I3 1 minus. I want to know what is the shape of this molecule, and obviously the hybridization. Take your time. Go for the structure. Okay, maybe this is a little difficult. We'll come back to this later. Answer this. I have NH4 plus. Tell me, what is the hybridization? What is the shape? Ammonium ion.
SP3, sir.
SP3, good. Yes, it is SP3. Right? Okay. Right. What is the shape?
Tetrahedral, sir.
Very good. Very good. Oh my God. Yes, yes, yes. So we know how to find the. Yeah, it is tetrahedral. Correct. Right. So we know how to find the hybridization. But again, I told you not to use this trick in your paper. You can use this somewhere, but you show that you know you are actually doing the hybridization. But I told you how to find out. There is something called a steric number, right? The steric number is equal to what? Tell me, what is the formula?
Number of atoms bonded to the central atom.
Okay.
Plus number of lone pairs in the central atom.
Correct. Right. So it is number of atoms bonded to the central atom plus the number of lone pairs on the central atom. Now, in this case, nitrogen is the central atom, right? And you have 4 hydrogen atoms attached to it. And obviously, you can see that there will not be any lone pair. Okay. So please understand, if you draw the Lewis dot structure, I know, see, you can understand that. See, there are 2 ways of looking at it. Okay, drawing the Lewis dot structure for NH4 plus. I think we even discussed it before. There are 2 ways of looking at it. One, giving the positive charge to hydrogen. One is, so out of the 4 hydrogens, one of them is H plus, right? And the other way of doing it is giving the positive charge to nitrogen. But again, that is wrong, but still you will be able to get the structure out, right? So you can do it in either way. Say, for example, if I give the positive charge to nitrogen, so I know nitrogen has 5 valence electrons. If I say N plus, that means I have only 4 valence electrons. So 1, 2, 3, 4, and each of the hydrogen will have 1 electron. So yeah, done, right? This is one of the ways by you doing it, right? Now, if I consider the hydrogen to have positive charge, okay, now what is the special thing which will happen in the structure? Tell me.
Coordinate bond is formed.
Exactly, right? So, right. So if I say that one of the hydrogens are H plus, there is no, I mean, hydrogen has 1 electron, so H plus will have no electron. So hydrogen, hydrogen, hydrogen with 1 electron, 1 electron, 1 electron, and obviously no, nitrogen has 5 valence electrons. So these 3 hydrogens, no problem. And I already have octet satisfied for your nitrogen. So obviously for this, these 2 are going to be in the form of a coordinate bond. Good, right? So yeah, obviously you see that the steric number is 4. There are no, you can see that there is no lone pair in either of these structures. You see that there is no lone pair on nitrogen. So 4 plus 0 is 0. Sorry, 4 plus 0 is 4. So definitely it is going to be sp3 hybridized. And since you don't have any lone pair, if I have sp3 hybridization, definitely the geometry on shape, both of them are going to be tetrahedral. Good, good. Okay, now since you have answered this, answer this. I3 minus. What is the hybridization of the central iodine? There are 3 iodines, obviously we talk about only about the central atoms. What is the central atom for, sorry, what is the hybridization for central iodine and what is the shape? sp3d, good, good Vanisha. Yes, it is sp3d. What is the shape?
Shape is linear, sir.
Very good, right? So yeah, shape is linear. Okay, so like this kind of molecules you will not be able to directly tell, right? So you have to draw the Lewis dot structures for this for you to answer this. Right, so I have 3 iodines and one of them is I minus, right? No problem. Okay, so I know iodine has 7 valence electrons, and if it is I minus, I already have 8 valence electrons. So let me put 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, and another iodine. 1, 2, 3, 4, 5, 6, 7. Right. So for these 2, no problem. Cool, right? So obviously, what this is gonna do?
It will form a coordinate bond.
That's it, right? So obviously, one of the lone pair will be donated to this iodine. So you can ask me, sir, octet is not valid. I told you, octet is not the only criteria, right? I can have molecules which can have more than 8 electrons in the valence shell, less than 8 electrons in the valence shell. All these things are possible. So this is the structure. So you can easily see, definitely, if you go for the steric number, there are 2 iodine atoms attached to central iodine. And we'll see how many lone pairs. 1, 2, 3. 3 lone pairs. So 2 plus 3 will become 5. And when I have 5, definitely, as Vanisha said, it is going to be sp3 dehybridization. Okay. Now, if at all I have sp3 dehybridization, what is the geometry?
Trigonal bipyramidal.
Good, right? So when I have sp3d, the geometry is trigonal bipyramidal, and we know how is it going to look. Say I have a, so I have two types of bonds, isn't it? I have something called as equatorial bonds, and I have something called as axial bonds. Correct, right? So obviously this, and this are my equatorial bonds, and one at the top and one at the bottom are what are my axial bonds, that they're in the same plane. Correct. Okay. So now if I have lone pairs, there was a rule. That rule tells me where should I put the lone pairs. What was the rule, and what was the name of the rule, and where should I put the lone pairs? At least if you don't remember the name of the rule, at least you can tell me what is the rule. So there are only two options, right?
It's bond rule.
Bend's rule. Okay, almost right. Right. It's called Bend's rule. Okay, fine. What does it say? Where should I put the
Lone
lone?
pairs must be in equatorial bond.
Good, right? So lone pairs, if you in trigonal bipyramidal geometry, the lone pairs must be placed in equatorial position. Only then you will get linear, right? So obviously you can see that there are going to be three lone pairs. So if I place the three lone pairs here, and forget that the lone pairs are there, and I have to put two other bonding atoms, you can definitely see that this is going to be linear, and that's exactly what is happening here, right? So I3 minus, the shape would be linear with sp3d hybridization, and you have to know that where I'm gonna put the lone pair. Only then you can get the shape. I told you, you don't have to mark up anything, right? You have to understand the rules. So if at all there are more electronegative atoms, say for example, if I have TCl3F2, I told you, again, same Bent rule, the more electronegative atoms should be placed in the axial position, and the lone pairs has to go to the equatorial position. Correct? So by this, I'll be able to easily get the shape of this molecule to be linear. Is that okay? Right? So fine. So I have to correct your papers yet. I didn't even start your correction of papers. You wrote periodic table. Right? So I will correct it. How many of you wrote the test? I think almost all of you took it. Right? So anyways, I will correct it and give it to you as soon as possible. Right? And the next test which you will be writing after periodic table, will it chemical bonding? Is it okay? But chemical
Yes.
bonding not the entire chapter. Chemical bonding is so huge that I can give it to you in 2 parts or 3 parts. Like say, starting with ionic bonds till VBT. VBT is your valence bond theory, right? And then I can have exclusively one for VST-PR and theory of hybridization. And the third part can be for your molecular orbital theory and hydrogen bonding and all the other types of bonds, that is your secondary bonds, hydrogen bonding, dipole, right? So anyways, I'll plan and let you know whatever it is. Okay. So fine, people. So we'll see day after tomorrow, right? Bye-bye. Thank you.
Thank you, sir.
Thank you, sir.
Thank you.